Welcome to Chapter 9 of Using Statistic Oxford series. In this chapter, we explore the foundational concept and methodologies of hypothesis testing. This powerful statistical tool helps us decide whether there is enough evidence in a sample to support a specific claim about a population. So, this chapter will cover a core principles, practical applications, potential pitfalls, and modern tools that aid in making data-driven decisions. So, the first section is the fundamentals of hypothesis testing methodology. So, this is the null and the alternative hypothesis. So, we start with the foundation of hypothesis testing, the null hypothesis, and the alternative hypothesis. The null hypothesis asserts that there is no effect or no difference in the population, serving as the default assumption. The alternative hypothesis claims the presence of an effort or difference that we seek to support through evidence gathered from the sample data. Then next is the critical value of the test statistics. So the critical value defines threshold that separate the acceptance zone from the rejection zone for our null hypothesis. This value depend on the distribution used, commonly the Z or the T distribution, and the significant level, typically set as at 0.05. When the test statistics exceed this critical value, the null hypothesis is rejected. Regions of the rejection and non-rejection. So, this critical value established two key regions. So, the rejection region and the non-rejection region. If the calculated test statistic falls in the rejected region, we have enough evidence to reject the null hypothesis, otherwise it remain accepted. So the risk in decision making using hypothesis testing. So hypothesis testing inherently involve two types of error. The first one is the error is rejecting a true null hypothesis, while the type 2 error is the false negative, which is falling to a rejected false null hypothesis. So balancing this risk is critical to make a sound statistical decision. So the section 2, which is the hypothesis testing approaches. So the critical value approach is this classical method involves comparing your test statistical to the critical value derived from the chosen significance level and distribution. So if the test statistical if the test statistic is more extreme, you reject the null hypothesis, or otherwise you do not. And the p-value approach is the p-value approach evaluates the probability of obtaining a test statistic at least as extreme as the one observed, assuming that the null hypothesis is true. The p-value below the significance threshold leads to rejecting the null hypothesis. So the connection between confidence interval and hypothesis testing is the confidence interval offers a range of plausible values for the population parameter, when a confidence interval includes the hypothesized value of null hypothesis. It corresponds to rejecting the null at the associated significance level, demonstrating the instrict link between the two concepts. So, can we know the population standard deviation? So, In practice, the population standard deviation is often unknown, especially with the small or incomplete dataset. When it is unknown, we can typically use the sample standard deviation and the t distribution for hypothesis testing. And that's all. Thank you. Then other member will proceed to another remaining section.
Section 3. The t-test for the mean when population standard deviation is unknown. The critical value approach with t-distribution when the population standard deviation is unknown, the t-test becomes appropriate. Here, critical values come from the t-distribution with degrees of freedom based on sample size. A test statistic behind this critical value leads to rejecting the null hypothesis. So in here, since our ABM 44, we sell Chaya Moringa cookies. So I will use that an example. So let's say that we were testing whether our Chaya Moringa cookies businesses earns more than a certain average profit. So, however, we don't know the population standard deviation if how much profits usually vary in similar businesses. So in this case, we will use a t-test instead of z-test. The t-test helps us decide if the difference we see in our sample, like average profit, is real or just due to chance. We compare our calculated result test statistics to a critical value from the t-distribution table based on our sample size. If the result is more extreme than the critical value, it means that our findings are significant and we reject the null hypothesis, which usually says there's no effect or difference. The p-value approach with t-distribution. The p-value is calculated based on the t-distribution, comparing the observed statistic extremity. This method provides a more precise measure of evidence against the null hypothesis. The p-value tells us how likely it is that our sample results, like our cookie sales, happen by a random chance. So a p-value usually less than 0.05, that it means it's very unlikely that the result is due to chance, so we can reject the null hypothesis. So a large p-value is more than 0.05, so it means our result could just be random, so we cannot reject the null hypothesis. Checking the normality assumption. A key assumption in t-testing in the data comes from a population approximately normally ensures the validity of the test results, especially for small samples. So, section 4, the one-tail test. For directional hypothesis, one-tail test focus on testing for an effect in a single direction which may offer higher power but require that the direction of the effect be specific in advance. So, a one-tail test checks only the one direction, whether it is greater than or less than. So it gives more power to detect a difference in the direction we expect, like higher sale rather. So, but we must decide beforehand which direction we're going to test, like it is to increase or to decrease. The critical value approach. The critical value for a one-tail test corresponds to the chosen alpha level concentrated in one tail of the distribution. So when doing a one-tail test, we decide on a significant level, often called like 0.05 or 5%. So this represents the risk you're willing to take in wrongly claiming a result is significant. So the critical value is a cutoff point. It separates common results from rare results. So if our test result is beyond this value, 0.05, it means that the effect is strongly enough to be considered statistically significant. So in one tail test, this cutoff is all on one side of the curve, left or right. So depending on the direction that we're going to test. So next is the p-value reflects the probability of observing an effect as extreme or more extreme in the specific direction under the null hypothesis.
So section 5, which is z-test for proportion critical value approach for the proportion. So when testing populations proportion, a z-test is used to determine whether the observed sample proportion is significantly differs from a hypothesized and population proportion. So this is done by calculating test statistic, which is the z, and comparing it to critical values from the standard normal distribution. So the critical values depend on the significance level known as the alpha, usually the 0.05. So and whether the test is one-tailed or two-tailed. So if the test statistic falls beyond the critical values, we reject the null hypothesis. So p-value approach for the proportions is the p-value approach. It involves calculating the probability known as the p-value of obtaining a simple proportion as extreme as the one observed. So assuming the null hypothesis is true. So if this p-value is less than or equal to the chosen significance level, which is commonly the 0.05, we reject the null hypothesis. So this approach provides a direct measure of how surprising or unusual the sample result is under the null assumption. So in section 6, which is its potential pitfalls and then the ethical issues in hypothesis testing, is the hypothesis testing can be misused in various ways, so such as misinterpreting p-values, using too small a sample size which reduces the test power, or engaging in data dredging, which is searching for pattern without a clear hypothesis. So these issues can lead to incorrect conclusions. So ethical issues arise when researchers fail to be transparent about their method. So exaggerate findings or make claims not supported by the data. So scientific integrity requires honesty in how hypotheses are formed or how data is analyzed and then how results are reported.
So good day everyone. So here I will be discussing to you the section 7 and section 8 of the hypothesis. So first is the section 7, which is the power of the test. So the power of a hypothesis test is the chance that it correctly finds a real effect. So meaning it rejects a false null hypothesis. And the powerful test helps you avoid missing through result. So power depends on how big your sample or how strong the effect and the significance level or the how strict your test is. So when planning a test, it's important to increase power while keeping the chance of a type 1 error or a false positive low. So next is the section 8, which is the practical tools, Excel, and Minitab guides. So software can make hypothesis testing easier with the Excel that has built-in functions to help you calculate test statistics, p-values, and critical values for different tests. Next is the Minitab guide. It is even more user-friendly for statistics It shows results with graph, checks assumptions for you, and help you explain your findings clearly.
So in continuation, I'm going to show you a calculation about C-test for the mean and the standard deviation is known. First is I'm going to give you an example problem. A machine fills bottles with an average volume of 500 ml. The standard deviation of filled volume is known to be 10 ml. A sample of 30 bottles is taken and the sample mean volume is found to be 495 ml. Test at the 5% significance level of the machine is under filling bottle. So first, we're going to identify the hypothesis, the standard deviation, the sample size, sample mean, and our significance level. So as you can see at our PPT, our hypothesis, population mean equals 500 ml, and our null hypothesis, machine is under filling, is population mean is greater than 500 ml. Then our standard deviation is 10, our sample size is 30, and our sample mean is 495, and our significance level is 0.05. To calculate the t-stat, the formula is z equals sample mean minus the population mean equals the population mean over standard deviation divided by sample size, square root of sample size. So you're going to distribute our sample mean is 495 minus the population mean is equal to 500, and then over 10 the standard deviation divided by the sample size, which is 30. So the 495 minus 500 equals negative 5, and the 10 divided by square root of 30 is equals to 1.8257 equals negative 5 divided by 1.8257 equals negative 2.73. To identify the t-stat, our population mean is to 500 and our significance level is 0.05. We are going to identify it using the t-table, which is negative 1.645. So the next example is the z-test for the mean. The standard deviation is unknown. So the problem is, a factory claimed its bulb lasts 1000 hours on average. A sample of 25 bulbs has a mean life of 980 hours and the sample standard deviation of 80 hours. So, using a 1% significance level test of if the bulb lasts less than claimed. So first, we are going to identify the hypothesis, the sample mean, the standard deviation, the sample size, and our significance level. So our hypothesis is 1000 and our sample mean is 980 and our sample size is our standard deviation is 80 and our sample size is 25 and our significance level is 0.01. So to calculate, there is a formula that z equals sample mean minus population mean divided by standard deviation square root of sample size. So our sample mean is 980 and our population mean equals 1000. So 980 minus 1000 divided by standard deviation, which is 80, and divided by square root of n, which is 25. So equals negative 20 divided by negative 20 over 8 divided by 5 equals negative 20 divided 16 equals negative 1.5. To solve the t-test or using the t-table, our value is equal to negative 2.33. So since our z equals 1.25 is greater than negative 0.33, so it means it's failed to reject hypothesis.
So good day everyone. So as you can see the next slides, there's another problem solving. It's a problem solving for t-test for a proportion. So the problem is an online retailer claims that the 60% of the customer are satisfied. In a sample of 100 customers, 54 indicate satisfaction. Test at 5% significance level if the true proportion is different from 0.60. So, as you can see in the screen or in the PowerPoint presentation, there is a steps on how to calculate the z-test for a proportion. So first step you have to do is to define hypothesis. So as you can see in the slide, there's two hypotheses, which is the two-tailed test. So the one hypothesis is equal to 0.60 and the one is not equal or not equal to 0.60. So the next step you have to do is known values. So as you can see in the slide, n is the sample size, which is 100, yung 100 customers. So next is the sample proportion, which is we have to divide the 54 indicate satisfaction and the 100 customer to get the sample proportion. The next one is letter A. A means the significant level, which is 0.05. So asa na siya nakuha, which is the 5% significant level. So you have to divide in 100. So the next step is compute the standard error. So as you can see in the slide, there's a formula, which is SE is radical sign, which is the kanang hypothesis, open and close 1 minus hypothesis and divide to n. So you have to change those sign into the given values. So as you can see, the our standard error is 0.049. So the next step is you have to do is calculate z statistic. So naagian naman nato na sa past activity, so you should follow na lang the formula. And our z statistic is negative 1.22. So the next one is critical values. We have to identify our critical value. So as you can see in the slide, we have the two-tailed test, which is our critical value is positive and negative 1.96. So look up at the 97.5 percentile, since 100% is minus 2.5% is equal to 97.5. So in standard normal distribution, so the value is approximately 1.96. So that's why positive and negative 1.96. So conclusion, so the decision is, since negative 1.22 between negative 1.96 and positive 1.96, so failed to reject hypothesis. So not enough evidence to suggest that the proportion differ from 0.60 at 5% level. So inatuon lang siya pagkuha sa d-test proportion. So that one is the problem solving, which is the z-test for proportion in terms of the number of events. So in the previous slide, the problem solving is z-test for a proportion. So now is also same, but in terms of the number of events. So as you can see in the power presentation, there is a problem. So in a sample of 200 trias, a rare event occurs 30 times. Suppose the historical proportion of the event is 0.20. Test at 10% significance level if the event occurrence rate has changed. So how to calculate this one? So in the slide, there's steps, no? So the first step is also same in the previous problem solving. You have to define hypothesis. So as you can see, our hypothesis is equal to 0.20 and the one is not equal and not equal to 0.20. So same process also in the previous problem, known the values. The next step is known values, which is we have to identify the n is the sample size, which is 200, and x means the observed event. So as you can see in the problem, the given observed event is 30. And the A is significant levels is 0.10%. So the next step is you have to calculate proportion. So how to calculate proportion? So you have to divide the observant event and the sample size, which is the 30 divided 200 is equal to 0.15. So the next one is, if you get the proportion, the next steps you have to do is calculate standard error. So same process kanina, di ba? Ganun lang din yung formula. Same lang din kung paano nyo kunin yun. So our next standard error is 0.0283. And the next one is calculate test statistic. So kanina, yung yung sinabi ko is Z statistic. Also same as Z statistic, and the test statistic is also the same. So same process lang yan. So our dito sa last problem is our test statistic is approximately negative 1.77. So the second to the last step, we have to identify the critical value. So as you can see, the total test, our critical value is positive and negative 1.645. So how to get that one? So we look for the 95 percentile, because the area to the left is of Z is 1 minus 0.05. So 1 minus 0.05 is equal to 0.95. So in standard normal distribution, consulting the standard normal distribution and statistical, the 95 percentile of the standard normal distribution is approximately 1.645. So the last step is the decision, which is negative 1.77 is greater than negative 1.645. So na-reject, no? Yung hypothesis natin is na-reject. So there is sufficient evidence proportion has changed from 0.20. So yung kanina yung previous problem natin is nag-fail yung rejection ng hypothesis, na-fail yung pag-reject sa hypothesis. Pero dito sa last natin, problem solving, is na-reject talaga natin yung hypothesis. So meron talaga siyang evidence of proportion, no? So ganun lang kung paano i-calculate yung z-test for the proportion in terms of number of events.
In conclusion, this chapter gave you both the knowledge and the tools for hypothesis testing, from basic ideas, methods to common mistakes, ethical concerns, and how to use software. With these foundations, you are ready to do clear, accurate, and confident statistical analysis.